In this section, we'll look at images formed in thin lenses. A lens is a piece of transparent material that uses refraction of light rays to form an image. Let's look at two types of lenses. Converging lenses are thicker in the middle than the outsides, and they're made up from two convex surfaces. When parallel light rays are incident on a converging lens, they will refract towards a point on the principal axis. A diverging lens is thicker near the edges than in the middle, and it's made from two concave surfaces. Parallel light rays that are incident on a diverging lens will appear to diverge from a point on the principal axis. When we go to draw a ray diagram for a lens, and I'll just show this with a converging lens, there's a few things you should draw first. Again, the principal axis, and then center the lens on the principal axis. Now we should draw the shape of the lens, but again we need a line to direct our rays towards, and this is called the plane of the lens. It's a line that's perpendicular to the principal axis and goes through the center of the lens. Now for lenses, there will be a focal point on both sides of the lens. The one on the same side as the object is called the near focal point, and then on the opposite side is the far focal point. I'm just going to label these both F because they're the same distance from the lens, but if you wanted, you could call them F and F prime or something like that, but they are at the same distance from the lens. So we have a piece of plastic or glass here that makes our lens, something that's transparent, and technically we know that light would refract at both surfaces, so from the air into the lens material, and then again back into the air. The thin lens approximation approximates that the light only refracts once at the plane of the lens. So instead it looks like this, where there's only one time where the light bends. And this is only an exact approximation if the lens is infinitely thin. However, it is a very good approximation for most lenses, which are fairly thin. And this is called the thin lens approximation, as I said, though there's a bit of glare on it, but I've written thin lens approximation there. Just like spherical mirrors, spherical lenses, or thin lenses, can form both real and virtual images. Because light rays pass through a lens, real light rays cross behind a lens, and so a real image is actually formed behind a lens on the opposite side of an object. A virtual image would be formed in front of a lens, and I'll show you both of these scenarios. Let's start by looking at ray tracing for converging lenses. Okay, let's look at ray tracing for a converging lens. So I've got my lens, the two focal points, and then O, and I'm not going to draw in C or R since that isn't a term we use for lenses. Now the first ray is the parallel ray, so it travels parallel to the principal axis, and this time it refracts through the far focal point. So let's just draw this in, parallel here, and then through that far focal point. Okay, and then the second ray is the focal ray, which passes through the near focal point and then refracts parallel to the axis. So I'm going to take the top of the arrow and go through that near focal point, hit the plane of the lens, and then refract parallel. So turn my ruler to parallel, and it passes through there. Okay, I only do 3 rays for lenses, so we do want to draw all of them in order to find the image. Here's the third one, the center ray. This one's easy. It will pass through the center of the lens and remain along that line, so it will refract on the same line. Okay, so like this. Okay, so let's look at drawing these for a real image on a converging lens. Again, we're going to draw 3 rays to locate the image, and where they cross is the image point. So my first ray is here. That passes through the far focal point. Now I have this ray through the near focal point, which then goes parallel. And lastly, the center ray, right through the center of the lens. Okay, it looks like it is going to meet in the right location through the image point. And then my axis is a little bit short, so I'll just extend that. And then you want to draw the image arrow as before from the principal axis down to where the light rays cross. And so real light rays here are passing through the lens. They do cross at this point, so this image would be real. A real image for a lens forms behind the lens. We can calculate the image position and the magnification for an image formed from a lens, and the equation is called the thin lens equation. So 1 over f equals 1 over do plus 1 over di. And I know we've seen this before and we called it the mirror equation. It actually does have a different name because now the sign convention is just a little bit different. The magnification is still the same and the signs for the magnification mean the same thing. So greater than the size of the magnification greater than 1 is magnified, less than 1 is reduced, and then a positive magnification is upright and negative is inverted. That's the same as for a mirror. Okay, the signs for the thin lens equation, DO is in positive in front of the lens, and really we'll always call the side the object is on the front, so that will be positive. And then DI, DI is still positive for real, but now this means that the object is behind the lens. DI then is negative for a virtual image which forms in front of the lens, so that's the biggest difference here. The focal length is positive for a converging lens and negative for a diverging lens. Example 6, a flower 4 centimeters in height is 200 centimeters from a 50 centimeter focal length converging lens. How far from the lens should the camera's light detector be placed? What is the height of the image formed on the detector? Okay, let's calculate this first and then we'll draw a ray diagram. So we have 1 over f equals 1 over do plus 1 over di. So di will be 1 over f minus 1 over do, so 1 over 50 minus 1 over 200, which is 66.7 centimeters. And that's positive, so it's going to be real and behind the lens. And then the magnification is negative di over do. So negative 66.7 centimeters over 200 is negative 1/3. And then the height is the magnification times the object height. So negative 1/3 times 4, which gives 1.33 centimeters. And now we can check this with the diagram. I've got my grid here. If you want to use this again, it's at the back of the Module 5 lecture problems. So here's the lens, and then the focal length, I've marked 50 centimeters on either side of the lens, and the object is here at 200 centimeters. We do need a scale on this vertical axis, so I've gone with 2 centimeters each, so we have a 4 centimeter high object. And let's draw the 3 rays. So here's the parallel ray first. Going to go parallel to the lens and then refract through that far focal point. Okay, and then the focal ray, so that's going from the object arrow to the focal point. It will hit the plane of the lens and then refract parallel to the axis. So I'll do my best to get parallel here. There. And lastly, the center ray from the top of the arrow through this midpoint of this lens where the plane and the axis meet. Okay, and the 3 rays meet at this point. Actually, that worked out pretty well. That looks like it could be about 66.7 centimeters, and that's the image. So we knew this already from the calculation, but we see that this is going to be real. Since real light rays pass through and cross at the image point, if we put a screen there, it would show on a screen. And it's reduced and inverted. Example 7, a magnifying glass is a converging lens. One particular glass has a focal length of 20 centimeters. Where should a stamp be placed to produce an image 4 times as large as the original object? Okay, so we have the focal length and the magnification of 4. This is a magnifying glass, so we know if you've looked through one, we want the image to be upright, so that is going to be positive. And this means that it will be a virtual image, but let's calculate and see. So our magnification equals negative di over do, which is 4. So we have di equals negative 4 do. Since we don't know either one, we know they're on the same side of the magnifying glass though. So then 1 over f equals 1 over do plus 1 over di, which will be 1 over do minus 1 over 4 do. So we have 1 minus a quarter, which gives us 3/4, 3 over 4 do. So I'm at 1 over f equals 3 over 4 do. And we're solving for do here. So do will be 3f over 4. 3 times 20 over 4 gives me 15 centimeters. And that was the answer of the question. It was where should the object be placed? So let's also just calculate the image distance. Since we can here, we have di equals negative 4 times 15. So negative 60. And remember, this means in front of the lens. Okay, let's check with the diagram. Okay, so I've got the ray diagram mostly drawn, but I'll go through it. So we have the focal point at 20 centimeters on either side of the lens, and then the object here at 15 centimeters. I've drawn it small because I know it's going to be 4 times magnified. And then the 3 rays. So the parallel ray through the lens, so parallel and then refracts through the far focal point. This ray through the center of the lens, and then this last ray, well, the order doesn't matter, but this one appears to go through the near focal point. So to draw that one, I attach the top of the arrow like this to the near focal point and draw this way, and then refract parallel to the plane of the lens. Okay, and then we can see that these 3 rays diverge. So we need to extend them all back until they meet at a point. It's not that clear with how I've drawn mine the exact point, but we know it should be here. And it looks like they do meet there at 60. So this is the image point I. It might be just close to that point since we are approximating things like parallel. And as we direct everything with a ruler, there is always some error. But we have I there. And as we expected, this is magnified. It does look about 4 times. It's at 60 or very close to that. And it is in front of the lens, which is where a virtual image should form. So to write the characteristics for this one, we would have virtual, upright, and magnified. Similar to a converging mirror, we can notice that the object placement will determine the characteristics of the image for a converging lens. And I've written out a summary. You'll notice this is all very much the same as I wrote for that converging mirror. But if we have the object outside 2F, we don't say R or C for the spherical mirror since there isn't actually, for the spherical lens, since there isn't actually a nice relationship between the radius of curvature and the focal length. But after 2F, the image would be real, inverted, and reduced. At 2F, it's real, inverted, and the same size, so twice the focal length there. And then between twice the focal length and the focal length, that's where if we place the object there, the image would be real, inverted, and magnified. And then at the focal point, again, that object forms an image at infinity, which I explained before. And then if we bring it within the focal point closer to the lens, we have an image that's virtual, upright, and magnified. No matter where the object is placed, diverging lenses always form an image that is virtual, upright, and reduced. Remember now that since this is a lens, a virtual image forms on the same side as the object. Okay, now let's look at ray tracing for diverging lenses. The first ray I'm going to go through is the parallel ray. This travels parallel to the principal axis and then appears to diverge through the near focal point. So I'm going to draw my parallel line here, and then it will diverge through this near focal point like this. So it still passes through the lens. I can extend that back. through the near focal point. Okay, now the focal ray, this one's going to move towards the far focal point and then refract parallel. So connect the top of the arrow to the far focal point with your ruler, and we'll send our ray there. When it hits the plane, we switch the ruler so that it will move now parallel to the principal axis. I'll extend it behind the lens since I know that it's going to diverge and produce a virtual image. Okay. And then one more. Again, I only do 3 rays for the lenses. So here's the center ray. This one is exactly the same as for the converging lens. So it goes from the top of the arrow through the midpoint of the lens here, and it's undeflected. Okay, let's draw all 3 and locate the image. So I'm going to have first my parallel ray goes parallel and then diverges through this near focal point here. And the focal ray looks as if it's going towards this far focal point, and then parallel, and the center ray lastly through that midpoint. And we could extend it along the same line. That's why we are looking for that intersection, which is right in here. And that's the image point. So the image formed by a diverging lens will always look like this. Essentially, the ray diagram is always the same, and we get an image that is virtual on the same side as the lens of the object, of the same side as the object from the lens, and then it's going to be upright and reduced. Example 8, a diverging lens has a focal length of 2.4 centimeters. Where should an object be placed to produce an image with a magnification of 0.5? So this is not incorrect. Often the focal length, if it's just said in a sentence, will not have a negative sign with it. So we do need to remember to add negative since it's a diverging lens. And then the magnification is 0.5, which is negative di over do. So di is negative a half do. Now we can plug this in and solve for do. So this will be 1 over do minus 1 over 0.5 do, which is 1 over do minus 2 over do. So negative 1 over do. And because of this, we get f equals negative do. So do is 2.4 centimeters. So we're actually placing the object at the focal point in this case. Okay, let's look at the ray diagram. Okay, so using this scale, our object and focal length are very close to the lens through the diagram, about 2.4 centimeters. I probably exaggerated that a bit, but let's draw the 3 rays. So first, we can do the parallel ray, going from the top of the arrow to hit the plane, and then that's going to appear to diverge from the focal point. So we can move that down to the object point and the focal point and continue that here. Okay, and then the focal ray looks like it's going to this far focal point. Basically the same diagram we just drew, right? So here, and then parallel. And it's looking right. We're getting a small reduced image here closer to the lens because the magnification was 1/2. So we'll end up with di is a half do. So, and then the last one is this center ray. And the image is right in here. So our whole diagram is very condensed, but that does look as expected. In the next section, we'll look at a few optical devices and how to combine more than one lens.